the second module. Welcome to that, to the fundamentals of electrical engineering. This time we focus on electrical machines. So here this is the second module, though according to the scheme of things that were planned earlier, this was planned to be in the third module. And there are two sections for DC machines themselves, and we are still on the first section, but we are moving into the fourth session. And in the fourth session, some focus on loss, efficiency, etc. are given, and other aspects that have been tried and tested in the gate examination is also covered as much as is possible in this session. Okay, so let's start off with some of the, most of these problems might give you a few consolidation of certain ideas that you already have, or you might discover yourself, okay, through these sessions if you are listening to them. Okay, so let's move to the first question. 50 kilowatt, the problem associated with machines happens to be that electrical machines with respect to the context of gate examinations happens to be that there's a lot of reading involved. Okay, that's the reason why when you're reading, I suggest that you compartmentalize and start visualizing whatever you see. Okay, so that machine should also always be in your mind, and the kind of machine, is it a motor, is it a generator, first and foremost, then is it a series motor or a shunt motor, or if it by any chance it happens to be a compound machine. Okay, and it's a motor or generator, like I said earlier. Yeah? Okay, and then the 4 or 5 equations formula that had been already dealt with. Okay, so now let's look at the question. The first question, the 50 kilowatt DC shunt motor. Okay, so it has been registered. It's loaded to draw rated armature current at any given speed. Okay, so it will draw the same current at any speed, and that too happens to be the rated armature current when driven at half the rated speed by armature voltage control. So what are we doing? We are reducing the voltage, okay, such that it can run at half the rated speed. Okay, so the input is reduced. Okay, if the input is reduced, the output automatically will be reduced. Okay, and so what is asked is, okay, there's another situation at 1.5 times the rated speed by field current. Okay, so now the field current is weakened such that the machine can run at a higher speed. Okay, but perhaps the supply has not been tested at all. Okay, so what has happened? Let's see what has happened. And the respective output powers, okay, so at 1.5 times the rated speed by the field control, the respective output powers delivered by the motor are approximately, so there are 4 options. Okay, in 2 options for the first question, it says that half the power load is delivered. True. Why? Because we realize that only the input is halved. If the input is halved by reducing the input voltage, no doubt that the output will also be halved. Okay, so approximately 25. Okay, so A and B should be right. One of them will be right. C and D are rejected. Okay, now let's look at the next portion. Okay, at 1.5 times, what has happened is that the voltage is not reduced. The flux is reduced. If the flux is reduced, okay, the supply voltage is not reduced, since the flux is reduced, the voltage is all available, and so what happens is that the back EMF reduces, but the current increases because voltage, the applied voltage is the same, the back EMF is reduced, so the compensation is via the larger current, such that larger drop can happen on the armature resistance. So again, the output remains the same because though EB has reduced, accordingly IA has increased. Okay, and of course we have not changed the input as well. So so obviously the output power remains the same and it's equal to 15 kilowatt. Okay. Moving on to the next problem. So what is it? Second, to conduct load test on DC motors. Okay, it is coupled to a generator which is identical to the motor. So we have 2 motors, they are coupled together. So they run at the same speed because they share the same shaft. The field of the generator is also connected to the same supply source as the motor. So again, field flux is also the same. Okay, the armature generator is connected to a load resistance. So I hope you have started visualizing the motor supplying the motive power, and then the generator supplying the electrical power to a load resistance. The armature resistance is 0.02 per unit. Okay, so it's called given in per unit. armature reaction and mechanical losses can be neglected. Okay, so that's all that we can do, because those things need to be measured otherwise. With rated voltage across the motor, the load resistance across the generator is adjusted to obtain rated armature current in both motor and generator. So the same current remains the same, okay, in both the machines. Okay? The resistance of the generators adjusted to obtain rated armature current in both motor and generator. The per unit value of this load resistance is what is being asked. Okay? So here quite a lot of understanding that we have. Okay, again, concepts are very important. So what do we have here? We have the same back EMF for both machines. Why? Because the speed remains the same. Okay, the speed is, they are coupled together. Then both the field is also and they are identical for one thing, and moreover the flux is also the same, because the field is connected to the same supply. Okay? So we see that E remains the same. And what is E for the motor? It is the same as equal to the applied voltage V minus I, the current that it draws, which is the same current as the generator current, multiplied by 0.02, which is the armature resistance, which is the same as equal to E, which is the same as equal to the total current, to the total drop on the generator, or the total load on the generator, which is equal to I into the same old I multiplied by R plus 0.02. R happens to be the load that is connected, and 0.02 is the armature resistance. Okay, I suppose this particular equation, which is different from all that we have studied, is very clear to you. Okay, if that is the case, then you can divide throughout by I, and so you get V by I as equal to R plus 0.0204. Why do we divide throughout by I? Such that we can get VI. What is meant by VI? This is the load. This is in terms of the per unit, the load that the machine is taking. Which machine? The generator is taking. Ultimately, V is given such that I can be drawn, and then you can have what is called as a load being delivered. And that load is equal to R plus 0.04, where R is the generator load. And so R is the same as equal to 0.96. This is actually the real internalization of the concepts that are there for any machine, because a machine is isolated in terms of what is happening there. So they work in tandem, and most of the losses are removed. So the only thing that is happening is transfer of energy from the electrical energy to, again, conversion to electrical energy. And so you're equating both, and you're getting such a situation, remembering that both have the same back EMF. Why? Because the speed as also the flux remains the same. Okay, so moving on, the concept rich question. Okay, moving on to the third question. The armature resistance of a permanent magnet DC motor, so field remains constant, is equal to 0.8 ohms. Okay, yeah, the armature resistance is equal to 0.8 ohms. At no load, the motor draws 1.5 amps from a supply voltage of 25 volt and runs at 1500 rpm. So everything associated with no load is given. That is, it draws 1.5 amps. From a supply voltage of 25 volt and runs at 1500 rpm. The efficiency of the motor while it is operating on load at 1500 rpm. Okay, so the speed is the same, drawing a current of 3.5 amps. Current has changed from 1.5 amp to 3.5. Okay, but of course it's not a no load condition, and then efficiency is asked. So there's a no load loss, and then there is also what is called as a general output. Okay, so let's see the power input at load. Okay, so what is being input happens to be power input at load plus VI is equal to, which is equal to VI, which is the same as equal to 25 into 3.5. Okay, so it's a DC motor, so it's being given 25 volt and it's drawing 3.5 amps. So 25 to 3.5 happens to be the input to the motor. Okay, the electrical input. Okay, and then what is happening is that there is a no load loss. What is that? There is a no load loss. For that we need to find out what is EB. What is EB? At the time when no load was going on. Okay, so we are having 25 minus 1.5 into 0.8 because of the armature resistance, and so we see that that's equal to the EB multiplied by the current. Okay, that gives us 35.7 as the no load loss. Okay, so that can be that can be added to the output, or it can be deducted from the input to get the output. Okay, so that's only one loss. Another loss is the copper loss. When is the copper loss happening? When the machine is on load. Okay, and that's given by 3.5 square into 0.8, which is 9.8. Okay, so now efficiency is the same as equal to the output, which is equal to input minus both the losses. That is 87.5 minus 35.7 minus 9.8. The losses themselves happen to be bigger than, it becomes larger than 45 watt. Okay, and 87.5 is the input and 45 is going to be the loss. So the rest is alone available. Okay, it's less than 50%. So of all the options, efficiency is definitely less than 50%, and that's equal to 48%. But of course, you can calculate as 87.5 minus 35.7 minus 9.8 divided by input, which is 87.5, and find the ratio. Okay. So this is very simple. The only the fact of the matter happens to be that you need to realize that there is a no load loss, okay, which is catering to the iron loss as also the rotational loss, okay, and there's also a copper loss which is different for no load as also for being loaded. So loading at the time of loading we calculate the copper loss. The rest happens to remain constant, okay, because the speed is the same, okay. Otherwise it wouldn't have remained the same, okay. Moving on to the fourth problem. It's not a problem, it's just an examination of the theory that we have learned. We are seeing that neglecting all losses, the developed torque T of DC separately excited motor, okay, operating under constant terminal voltage is related to its output power. Okay, so there are various relationships shown between torque and power. One is the square root of power, another is direct proportionality, third is torque square is proportional to P cube, and torque is independent of P. Okay, so how do we start thinking? Okay, we start thinking and remembering that power developed is the same is equal to EBIA, which is the same as equal to 2 pi into 16, of which EB or EG is proportional to both speed and flux. Okay, and torque is also proportional to flux and current. Okay, so this is the interrelationship that we talked about earlier. Okay, so if this is the situation, then we can put them all together. How do we put them all together? We realize that now power is proportional to EBIA, where EB is proportional to flux and speed, and on the other side we are having speed and torque. Okay, so speed and speed can cancel, and now torque replaced by flux and current. So we see that we are having flux and current. So we see that flux is also on both sides. So it's simply torque is proportional to power, directly proportional to power. Okay, so this is again a use of the convoluted relationship between different quantities in a motor. Okay, so let's move on to a cumulatively compounded long. Okay, this is the first time that we are encountering a compounded machine, long shunt machine. So long shunt means even the series winding is included in the shunt field, is driving a load at rated torque and rated speed. Okay, so torque and speed are rated. Okay, if the series field is shunted by a resistance equal to the resistance of the series field. Okay, so we are now going to shunt the series field. What it means is that the content or the amount of current that is flowing through the series field winding reduces, or the flux reduces. Okay, by resistance equal to the resistance of the series field, keeping the torque constant, but still the torque is kept constant. Okay, so yeah, so what do? We it's running at rated torque and rated speed. Okay, so yeah, keeping the torque constant. So the only way is to keep the torque constant is to see to it that because the field is reducing, the back EMF has to increase, is also reducing. So since the flux is reducing, the back EMF is also reducing because it is being shunted. So now we have to provide extra voltage. Okay, and that's the reason why and that has to be taken care of by having an extra current flowing through the resistors, such that the applied voltage, because it's remaining constant, this can be taken up by the armature resistance. Okay, so we are having armature current increasing as a result of this. Okay, moving on to the last slide in this. Okay, it's looks like a machine. We are having C1 dash as one coil, and C2 dash as another coil, and the poles seem to be rotating. Okay, two magnetic poles revolve around a stationary armature carrying two coils, C1 dash, C2 dash as guessed and as shown in the figure. Consider the instant when the poles are in a position as shown. Identify the correct statement regarding the polarity of the induced EMF in this instant in coils C1 and C2. Obviously, since the poles are moving, and they are associated with the flux is associated with C1 dash and not associated with C2 and C2 dash. We don't have any EMF in C2 and C2 dash. We have an EMF in C1 and C1 dash. Okay? And in what direction? You have to use your right hand rule. Okay, the flux direction can be shown by your forefinger. The movement direction can be shown by your, that is, and take C1 as reference. and by your thumb, and then you will get the direction of the induced EMF there. Okay, so it's obvious that option A is correct, because there is no EMF in CT for one thing, and then the EMF direction is also shown appropriately with the dot. Okay, into means into the system. Here it just means away from. Okay, or it's emerging or towards the reader of the question. Okay, so I suppose this is a very short session, because we have covered several things, and most importantly we have covered some of the concepts, like for instance how torque becomes proportional to the power, so long as it's a DC, it's a separately excited machine. Okay, and it's also operating under constant terminal voltage. Okay, so then we see that there is no scope but for the torque to be proportional to power. Okay, so that's another one control that is possible. Okay, torque, power torque control. Okay, another is, of course, we saw that we are having the efficiency being calculated from two separate measurements. One was done at no load, and another was done at load. Okay, at load we realize that there is an input happening, and that from the input some losses need to be catered to, and so then we get the output. What are the two losses? One is the copper loss, which happens for the loaded condition, and then there is a no load loss, or the iron loss, and the movement, the rotation loss, etc. They are put together in the no load loss. Okay, so no load loss remains constant, so long as the speed remains constant, and flux is also remaining constant. It's a permanent magnetic field. Okay? So these are some of the things that we saw, and we also saw something with respect to something very different, in the sense that when a motor and the generator are coupled together, and they are running at the speed. Of course, the speed is the same, and the flux is also the same. In that case, you can, and the current is also the same, because the resistance is adjusted accordingly, and so you can put together a very special equation wherein it is the same. It is given as equal to V minus I into 0.02 equal to E, which is equal to I into R plus 0.02. Okay, in that manner R can be calculated. Okay. We also saw two different controls. The armature control, wherein the power also, if the armature voltage is reduced, the input is reduced, so the output also reduces. Okay? If the field is controlled and the armature is not done, we don't do anything with the armature, then armature current also increases, and so though back EMF reduces, the armature current correspondingly increases to deliver the same output. Okay? So I suppose this session is very appealing to you, because quite a large number of really different concepts were discussed, which of course adds to the earlier segments. So thank you.